Thanks for the introduction, Christian. Thanks to the organizers for inviting me to this great event. It's good to be doing something like this again finally, so thanks a lot. And it's really my pleasure to talk to you today about MEMS that we use for mixed reality displays, particularly ones that we use for the HoloLens products. And I don't know who here may or may not have heard of HoloLens, and in particular I'm going to talk about HoloLens 2. If you didn't know what HoloLens 1 was or 2, if you indulge me, I'll share some of our marketing videos just to sort of set the stage. Realizing there are some perks working at a company that makes video games, making this kind of stuff. But this stuff would have gone by kind of quick. But what's inside the display is what the rest of this talk is going to be about. There's red, green, and blue lasers that are combined to be able to make a bright display with a really wide color gamut. And then the display technology is kind of unique in that it uses micromirrors and scans these laser beams to fill in a 2D display. One more little video that shows about the use case for the product, because the previous one was showing the fish experience, but there's more to it. This mixed reality thing, once you get it on someone's head, then it's providing the ability to put virtual 3D content on top of the real world. So it's not virtual reality where you're totally immersed and not experiencing the real world. You're looking through, and everything is being oriented on top of the real world, and people can share it, and that's kind of the overall idea. And this started quite a while ago, actually now. 2016, HoloLens 1 was launched. And it had certain display specs. The field of view was 35 degrees diagonal. The maximum brightness that it put out was 350 nits. That's not that bright, and the field of view is not very big. So for HoloLens 2, pretty big improvements on both fronts. Field of view, diagonal field of view was increased from 35 up to 50, and the brightness up to 500 nits. That's getting into where it's more usable in daylight environments or bright artificially lit rooms. And this was all enabled, the increase in the field of view and the brightness was enabled by changing the display technology from LCOS microdisplays to laser beam scanning with MEMS. And there's history of using MEMS for displays. Here's some great examples. Some people in this room worked on some of these. It goes all the way back to '96, and of course this is still going. This was a pretty impressive milestone in the MEMS field. All of these are really great demonstrations. What they have in common is that each pixel is an individual active element. So every pixel needs something that you are controlling, one individual item that you're controlling. The other MEMS technology is laser beam scanning. I worked for a lot of time at Microvision, and something like an AR product goes back actually quite a long ways. This is one iteration that goes back to 2004. And then there was a bunch of Pico projectors work that came out in the 2015s. This was enabled by the maturity, finally, of red, green, and blue laser diodes in with light output power and form factors that could go into these kind of consumer products. So laser beam scanning is, it's not like a matrix, 2D matrix of pixels. Some people call it flying spot. It's really, there's one pixel, and you just move it around in time. And this is one implementation where you have a two-dimensional scanning built into one device. And so there'll be a mirror and two beams that allow the mirror to rotate like so. And that whole thing is suspended by a gimbal frame that has its own flexures that allow it to rotate up and down. And this horizontal one of these axes needs to be very fast, because to make the display look like it's not being modulated, it has to move very fast and then repeat at a high frame rate so that you don't perceive that actually this scanning is going on. And so really the only practical option is for one of these axes to be resonant. And so this diagram is meant to show how this looks. This spot will have a really high velocity in the horizontal direction headed this way. And usually the most kind of pleasing to the eye way to arrange things is to keep the velocity of the vertical scan constant. So it's tracing at constant speed, and you're painting these lines back and forth. Here's some examples, and I'll start to get into how the design trade-offs are working. There's kind of a famous relationship for this, like that sort of tells you what performance specs that you need to hit. And it's how you count the number of pixels that you can display in a given frame rate. And that number is going to be proportional to three parameters only. The theta is the scan angle. A larger scan angle will give you just more opportunities to show however many pixels of a certain size. So just count, if you have a small pixel that you sweep over an angle, you just count them up. So this dimension, just counting pixels in this direction. And then D, the mirror diameter. From diffraction theory, if you have a larger mirror, you will be able to focus a collimated beam into a smaller spot and give you more opportunities to densely pack pixels. So that's that one. And then the frequency, a faster scanning frequency will let you paint more horizontal lines as you go. And what's interesting is there's lots of ways to arrange things, and I guess I can show you one example just from these devices. This one in the middle is SVGA, so you get 800 pixels horizontally with a pretty large mirror. This one's giving you 1280, but the mirror is smaller, and that's because you've changed the way that the theta and the D are working together. This one's going to a bigger angle with a smaller diameter. So there's quite a bit of flexibility. Here's three devices that are all pretty similar sizes, but with very different resolutions. I'd like to share a little bit about the mechanical design for these scanners and how that is working. If you wanted to create the fast scanning function, we can do some quick hand calculations just to see how the trade-offs are working. Say you wanted a 2 millimeter diameter mirror, and you wanted to go to a certain scan angle at a certain frequency, and the certain frequency was going to be 30 kilohertz. So I now know the inertia of the mirror, and I know the frequency, so I just need to figure out what the stiffness of these springs are going to be. So that's just a number. And then I've got, say I had a 25 micron thickness to work with in a device layer, a silicon device layer. Then I've got the width and the length to play with. So one option to get that frequency would be a pretty short beam, 20 microns long, or 20 microns wide, 60 microns long. If I would do the hand calculation for the stress in that beam, I'd find myself too high, 7 gigapascals. Silicon maybe can theoretically withstand that stress, but in practice not. It has to be quite a bit lower. So I make it longer and wider. That spreads the stress out over more surface area in that beam. And with my hand calculation, I would say I was okay once I saw 0.8 gigapascals. But this is kind of too coarse to send to tape out. I've got too many sharp geometries here. They're going to concentrate stress. And so in these locations, there could be stress concentrations of factor of 3 or something like that. So you have to take it to finite element analysis. And what that will show is that we need to start adding fillets, spreading the stress over a bigger area. We have to get rid of sharp geometries. That's going to take my initial design, and it's going to force me to add stuff that takes up more space spreads the stress out and removes sharp geometries. So that's actually most of the design stuff for the fast scanner is coming around managing the stress in these beams. For the slow scan function, for the vertical scanner, that's not a resonant scan, that's a quasi-static scan. And the design of those turns out to be quite a bit more complicated. This is the trajectory that you want to paint, to have a pleasing spacing of the lines that we're using this scanning mirror to project. And I want a part that gives me lots of time to put those lines down with a constant velocity, but then I want to, this is one period, and so I want a really fast part. So I want to start over pretty fast and not spend too much time getting back to where I started, and then trace slowly and then snap back. So the trouble with this is if you think of the Fourier series or the FFT of this thing, it's going to have tons of harmonics. So say I was trying to do this with a 60 hertz repetition rate, a 60 hertz frame rate, then I've got lots of frequency content at the multiples of 60. And what's going to happen when I'm doing the design is I'm going to end up with a mode of vibration. In order to meet all this stuff, it's very typical to have a resonant frequency in the couple hundred hertz or a few hundred hertz, around 1 kilohertz range. And that's going to be right in the middle of where I'm trying to put all this stuff. And so there's a huge range in responsivity to whatever drive I'm doing here. So here's a factor of 3 orders of magnitude. And so what becomes challenging is the control of the tendency of this thing to want to oscillate there. It could be from vibrations or some external stimulus or some other noise is going to make that thing want to vibrate there. And I'm just showing one of the modes. It's pretty common to have many other modes. They could be like ones you would imagine as pumping or sliding or other kinds of rotation modes. And so this turns out to be one of the big design challenges. And when it's not managed properly, you end up with these artifacts in the image. I don't know how well you can see this. I played with the contrast of this picture. But this is a real picture from a display where this issue of having too much response at the resonance is making something ride on top of this, wiggling on top of this thing that was meant to be a constant velocity, disturbing that velocity and making the lines either bunched together or spread apart a little bit, and they appear brighter or dimmer, and that's how it looks. So that's some difficult control problems with this scanning function. And the way that's managed is by creating a control loop. And Silicon gives a really fantastic option here. What turns out to work really well for many years now is embedding piezoresistive sensors, implanting them in the silicon, and in a full Wheatstone bridge configuration, you can get very good linearity, for example, pretty good sensitivity. What you're trying to do is, let's imagine you were trying to put down 1,000 lines in the display. You're going to need about 1/10 of a pixel dimensions worth of precision in the control, so about 80 dB. So that the fidelity of the controller and the fidelity of the motion has to be really perfect. But this is a really great option. These things are, these sensors are embedded directly into the crystal lattice at high temperatures, and after they're there, nothing happens to them. They don't age. They don't have any real degradation mechanisms. For HoloLens 2, we ran into some limitations with the state of the existing technology up to that point, and it has to do with increasing the field of view and increasing the desired display resolution. And biaxial scanning turns out to kind of hit some limitation where it's hard to push it further. So just a kind of rough scale sketch here, where in blue is the horizontal scanner, in green is the gimbal representing the vertical scanner for a 1280 by 720 design. And if I wanted to increase the pixel count and increase the field of view somewhat, what's going to happen because of that theta df thing, and the fact that the fast scan design is driven by the length of the beams that's required to manage the stress, you end up with looking something like this. And now I'm wrapping this gimbal around something that's getting quite large. And this is something that I do need to be able to deflect to not have a ton of modes coming out of the vibration of this whole structure, the complete structure. These have to start getting stiffened up, and then they get hard to move. And so we've got just a lot of things that are escalating, compounding against each other. This is due to the combined inertia growing very fast. We have lots of modes of vibration coming in. You have to keep stiffening the flexures. The power consumption goes up. Shock robustness is always in the background driving things too. So the solution, and this was applied to HoloLens too, is to separate the scanning functions into separate devices. And schematically, that is like this. We still combine red, green, and blue lasers. Normally, before we went into a 2D mirror that addressed the image, and this is using two separate mirrors. So the beam first goes to a high-frequency 1D scanner, then to a low-frequency 1D scanner, then to the display. This starts to simplify things quite a bit. And we end up greatly reducing the kinds of interactions between parameters for two functions that are separate functions, but they are interacting. So we can more readily manage ancillary modes of vibration interfering with scanning behavior, crosstalk that you naturally have between axes on a biaxial device, and acceleration shock robustness. We don't carry the mass in one device of both a fast scanner and a slow scanner. So this allows for better optimization of each device, specific for its function. And one thing that's interesting about this is people, at least in my previous companies, we expected that this would be kind of bring a penalty of fewer overall die per wafer, but it's not necessarily true. Actually, often it ends up with kind of better die per wafer, and so production cost. Surprisingly, two devices can be cheaper than one device. Now about actuators. Once the basic mechanical design is in place, then we have to figure out how it is that we're going to make it move with precision. So, simple free body diagram. The slow scanner actuator, because it's quasi-static, the actuator really is just overcoming suspension spring stiffness. Damping is not really playing a role in the actuator design. Conversely, the fast scanner, because it's resonant, the actuator's only job is to overcome the air damping. And so stiffness is not a significant factor. Stiffness and inertia take care of themselves by resonating. Unfortunately, in the design process, these mirrors, there's no narrow gap like there is sometimes in MEMS that lets you do some calculations. It's very complicated fluid flow. So you end up, at least so far, we're resorting to kind of doing what they did for airfoils years ago. They just tested them and came up with these drag coefficient laws that you can plot against some sort of normalized parameter that lets you kind of scale different geometries. So you end up doing the same thing with these. And so it's an empirical guidance for doing the actuator design based on the amount of damping that it's going to have to overcome. Even though these devices are small, they're scanning really fast. And so you are definitely in turbulent flow regime. So even harder to tackle analytically. This is a 2014 view of the different actuator technologies that you could try. There's really only 3 practical options among the MEMS actuators: the electromagnetic, electrostatic, and piezoelectric. This chart is showing circa 2014 different theta df are these parameters that tell us what kind of resolution we have. We want to be high on this axis, and there's a little bit more flexibility on this axis, the frequency axis, but on these lines you're seeing the different kinds of display resolutions. And in 2014 it was starting to look like piezoelectrics had better reach into the high performance. Otherwise, the trade-offs between these different ones are pretty well known probably to this group. For example, electrostatic comb drives don't have much force, but they have pretty simple fabrication. moving coils have really large displacements and pretty good force, but for compactness, you have to have something that's generating a magnetic field external to the device that's going to take up space. So it's like this. And PZT is sort of like splitting the difference between some of these, but I think since 2017, some things changed, or since this chart was made in 2014, things changed. And since 2017, I would give PZT films, thin film PZT, an extra check in some of these. The fabrication, it's not as simple as comb drives, but by now, since 2017, there's places to get now. You can get the films. It's more readily available. And linearity is coming down to kind of overall structural actuator design, so less of a disadvantage there. And with this mechanism design, you can get large displacements out of these structures. So if I think about what would be the calls for action in this field, this movie is showing one of these actuator designs using PZT thin films. It would be materials and process technology in a couple of areas. On the actuator side, I just mentioned piezoelectric thin films. I think they're kind of emerging as the winner in the actuator world. And what would be great is some improvements that would create some budget for trading among some different performance trade-offs. If we could get larger transduction coefficients out of the films, we could make the actuator smaller, probably, or we could reduce the voltage, or we could do something else. If they had lower internal losses, you could reduce some power consumption. If they had better stability, you could translate that into reliability or performance over temperature. And if there was more industrial capacity, then it would just be easier to get started and to get implemented. And what's happened recently is, this became first available mostly with sol gel, which is kind of expensive and time-consuming and hard to get going. But now there's sputter tools that you can get in a fab for sputtering or for depositing these films. And the film properties are improving and surpassing sol gel. And it's that industrial capacity that is kind of making it more practical to use this option. So it's super impactful. On another one, I would say silicon is an area that would be nice to have some movement. Here's some pretty well-known charts about silicon in the stiffness world of different materials. Silicon is pretty good. In the strength, it's pretty good. I put a mark here for silicon. Of course, it depends on a lot of things. It supposedly would have about 7 gigapascals of theoretical strength, but in the real world, you end up getting somewhere around here. Diamond is up here somewhere, and man, it would be nice to be up in here. What you could do then is make devices smaller. I talked about how the device sizes are determined by the need to distribute stress in these flexible structures. Here's a view of the fracture stresses. Here's one part that we worked on, and the statistics of testing to failure. And in this process with this design, we got pretty reliably at least 1 gigapascal worth of fracture stress. So you have to design down here. If you could push this out a little ways further, you could really turn that into tangible benefits of cost or performance. And here, for fun, I have a movie of we test these devices to failure to figure out where we're standing. And boy, silicon is a brittle material, and when you get it at high stresses, it really shatters crazy. So it's fun with high-speed video. That concludes the talk. Thanks for your attention.
Thank you very much. Great presentation.
Thank you.
Are there questions? Please, as before, wait until you have a microphone. And it would also be nice if you can give your name and your affiliation before asking the question. No questions yet. Actually, I have a question. You mentioned. Oh, no.
We can measure the stress in thin film. Is that of interest, or is only in bulk material stress?
Thin films aren't very practical for these applications just because the dimensions of the stuff that has to be carried, these mirrors have to be pretty big. And to keep them flat, they got to be pretty thick. So it's really the bulk properties that we're most interested in.
Wyatt, great talk. Tim Brosnan from SEMI. You mentioned going from a single device that's a dual axis gimbal to two separate mirrors. What are the challenges there? How can you align them accurately enough?
Oh yeah, that's an assembly issue. So in assembling the display module for HoloLens 2, we use active alignment to build the projector, what amounts to the projector. But with active alignment, it's all achievable. But yeah, you have to monitor. You have to actually turn the mirrors on while you're assembling them, and then you can get things orthogonal and lined up.
Question over here.
David Lin from GE Research. Curious about the thermal consideration. I assume the laser power is fairly low. So for application, for example, if you have a high power laser, are you concerned about a lot of heat can be absorbed into the silicon and cause some issue?
Yeah, we use aluminum mirrors, and they're about 90% reflective for the wavelengths that we're talking about. I don't really have a good understanding of what the optical power handling limit of these before you would evaporate that film. If you want to do really high power handling, and you knew exactly what wavelength you were doing, you could maybe do a Bragg stack or something like that. That would be able to manage that. But these can handle quite a bit, but I don't, off the top of my head, know what the limit is.
Hi, Sudhanshu here from Purdue University. I have a question about fast scan and slow scan. Are you looking to replace both of them with PCT actuators or just the fast scan?
Yep, I think so.
Okay.
Yep.
Aaron Zilke from Rockley. Quick question about your lasers. What is the lasers you have now? Are they like FabriPro narrow line width or some other kind of laser? And then what kind of laser do you want ultimately in the future?
Cheap. Yeah, we use FabriPro laser diodes, red, green, and blue, commercially available laser diodes. Yep.
Time for one last question.
Thank you. Michael
Actually,
Helmbrecht.
one more thing, just since you asked. A little bit bigger wavelength, or a little bit wider spectrum would be helpful. They're too narrow.
Michael Helmbrecht, AI. Could you make a comment on the PZT, on the piezoelectric films, just in terms of temperature performance? Are you seeing the transduction parameters drift over temp, or any maybe long-term temp effects on the?
Yeah,
on those?
they definitely do, but hopefully they get better when they get hotter. So that's kind of counter to most things. So it's actually they're happier in a hotter environment. The temperature stuff to do with these things are mainly to do with the piezoresistive coefficients over temperature and how you compensate for that in the mirror controller.
All right, let's thank the speaker again.